Hello everyone, welcome to the session where I am bringing subtopics from different topics where I am sharing alternate ideas, short tricks to solve questions faster. In today's session, I will talk about Newton's identities and recurrence. This is taken from chapter quadratic. After knowing this, you will be able to solve particular type of questions faster. You will have different approach to look at those questions. Before I start, let me talk about 𝒉𝒐, who got All India rank 15 in JEE Advanced 2025. He got full 120 marks out of 120 in JEE Advanced Maths paper 2025. He was student of 𝒉𝒐 20 to 25. I was teaching him for 3 years. In fact, the brain behind these sessions, the ideas behind these sessions are from the discussion which I used to have with the batch of 𝒉𝒐. In fact, few ideas are coming from 𝒉𝒐 also. Okay, so the motivation here is to get students who can repeat the performance that was shown by 𝒉𝒐 this year. I am hopeful that many of you will be doing this thing next year. So bachcho, this is me, Surendra Jain. I am teaching maths for last 14 years. I am teaching students for JEE Mains, Advanced, Olympiad, CMI, ISI. Actually, I am still engaged with my students of 𝒉𝒐 and 𝒂𝒑𝒉 who will be writing JEE Advanced next year. And let's hope that we repeat the performance of 𝒉𝒐 this year also. But Shimon sir suggested that I should be sharing something to the students who are following him through YouTube. So these sessions started. This is a kind of extra work, I will say, but the kind of response I am getting from all of you is overwhelming. I am feeling very humbled, and I feel these sessions, this process of these sessions will continue for long. Okay, so let's start what I was talking about. So Newton's identities and recurrence relation in a quadratic equation. Actually, Newton's identity is a general thing for any polynomial. I will first talk about this in the context of quadratic, and I'll show you how a recurrence thing coming in the picture. Actually, recurrence relation is a big chapter in itself. Here I'll be using just small thing of it. Maybe some other session I will be talking only about recurrence relation. I'll tell you different type of recurrence relation and how to solve them. Okay, but here what is this Newton's identities? Please see, suppose we are given a quadratic ax square plus bx plus c is equal to 0 and its roots are alpha and beta. Okay, then if I define a sequence Sn, that is, let's say p into alpha power n plus q into beta power n. Okay, this is my equation 1 and this is equation 1.1. Okay, then we claim that this Sn for all n greater than or equal to 2 satisfies this quadratic. When I'm saying Sn satisfies this quadratic, I mean to say that I will put Sn in place of x. So when I'm putting Sn in place of x in the leading term, I will be writing it as Asn. But now, because the second term is having 1 degree less than the x square, so here also you will be having 1 degree less in Sn minus 1. Here Sn, you can say degree defined by the powers on roots alpha and beta. So this is Sn, this is Sn minus 1. 1 degree less, 1 degree less. Similarly, I think you can now guess the next term would be c into Sn minus 2 for further 1 degree less for Sn, and that will be equal to 0. Now you can see Sn is now connected, is having some relation with its two predecessor terms of the sequence Sn minus 1, Sn minus 2. So this is what we call recurrence relation, where every term is coming from the knowledge of two previous terms, like Fibonacci sequence, where first two terms are given and then next term is found by adding the previous two terms. Okay, so similar to this only. Now if you know S1, S2, you can find S3. If you know S3, S4, you can find S5 and so on. In fact, in this sequence, S0 also works fine. So you can make use of S0. In fact, S0, whenever you are writing, in this case, it will be P plus Q. Okay, because alpha power 0 will be 1, beta power 0 will be 1. So this is what Newton's identity is in context of a quadratic equation. Let me talk of a converse thing also. When we say converse, okay, when we say converse, that means we are given this relation, that recurrence relation. Now we want to know whether Sn will have a solution of this type or not. So suppose your 1.2 equation is given, okay, then also we say Sn will be only p into alpha power n plus q into beta power n, where alpha and beta are distinct roots of the quadratic 1. Okay, that means if this relation is given, then Sn will be only this thing, nothing else, where alpha and beta are distinct roots of this, and p and q can be found. P and q are found using S0, S1, S2. Any two of them are sufficient to find your P and Q. Okay, because you know alpha and beta, because that ABC is known. So quadratic solving you can get alpha beta. So only two unknowns are there. So if you know S0, S1 or S1, S2, you will be able to find P and Q also, and that P and Q will give you any number of term like S100 you want, you can find it directly. Okay, now two things. One, I said distinct roots. Okay, that is one is distinct root. One more thing, I think yeah, that thing was that how to find PQ, that I have already mentioned. So distinct root I said, but if alpha is equal to beta, okay, if alpha is equal to beta, then the solution will not be Sn is equal to p into alpha n plus q into beta power n, because beta is equal to alpha only. In this case it will be q into n into alpha power n. Okay, if alpha is equal to beta, once again p and q are found using S0, S1. Okay, I'll tell you how S0, S1 are found using one example. So suppose this is one recurrence relation we are given. 2Sn plus 2, 3Sn plus 1 minus 5Sn is equal to 0, and initial values are given. So here you can see the quadratic should be 2x square plus 3x minus 5 equal to 0. And very easily we can see roots are 1 and other root will be minus 5 by 2. So what we can say, the starting point will be now that Sn has to be some p into 1 power n plus q into minus 5 by 2 power n. Because now alpha beta are known, we have put the values. Now we want to know p and q. Now if we are given S0, that is 1, S0 is equal to 1 means it should be p plus q. Okay, S1 is 2, so if you put n is equal to 1, we will be getting p minus 5q by 2, putting n is equal to 1. Now if you solve it, subtract, so you get minus 1 is equal to, I think, 7q by 2. So the value of q will be minus 2 by 7, and if I put the value of p here, I think it will be 9 by 7. Okay, so what we are getting, that my Sn in general should be p, that is 9 by 7 into 1 power n. You may not write 1 power n, and then plus q, the value of q is minus 2 by 7 into minus 5 upon 2 raised to the power n. So that is the solution of this kind of recurrence relation, because roots were different. If roots were same, then you will not take like this, rather you will be taking like this, p into alpha power n plus q into n into alpha power n. Okay, now I would like to show you how it is a solution. Now suppose you were not aware of this kind of thing, you were given this relation only. So if using this given relation, if I need to find S2, S1 we already know. If I want to know S2, so I will put n is equal to 0. So this will be 2S2 plus 3S1 minus 5S0 is equal to 0. Now 2S2, S1 is 2, so this will be 6 here, minus 5 into 1 is equal to 0. So S2 is coming out to be minus half. Okay, now can you see that if you put n is equal to 1 here, if you put n is equal to not 1, I will be putting n is equal to 2 here. Okay, if you put n is equal to 2, what will this be? What will this give? S2 will be equal to I think 9 by 7, okay, minus 9 by 7 minus this will be 25 by 4, so 1 2 got cancelled, so 25 by 40. So this also gives you minus half. You can check 18 minus 25 is minus 7, so minus half. So you can see we are getting same thing directly without use of this recurrence relation, because suppose someone has to find S10, so you will keep doing this way, S2 then S3 then S4 S5 up to S10. But if you know this relation, I think S10 can be found directly. In fact, your Fibonacci sequence can also be found directly with the help of this method, although the calculation is not very clean, very neat. Here roots are decently good, so we can find any number of terms. If roots are not good, like they are irrational number or they are imaginary complex number, then again that will also not be very good idea. But yes, first you have understood how this recurrence method is working. Yeah, so I was actually talking about, I just forgot that I was about to tell you the proof, how it is coming. I think proof is very simple. If your roots are alpha and beta, so they should satisfy the quadratic. So a alpha square plus b alpha plus c equal to 0. Okay, because alpha is a root, and similarly a beta square plus b beta plus c equal to 0. Okay, now you can multiply this with p into alpha power n minus 2 and this q into beta power n minus 2, and if you multiply and then add the first term, if you add, it will be a common p into alpha power n plus q into beta power n plus b into p into alpha power n minus 1 plus q into beta power n minus 1, and similarly c into p alpha power n minus 2 plus q into beta power n minus 2. So you can see how easily it is coming. A into Sn plus b into Sn minus 1 plus c into Sn minus 2. But please remember, this will be true if n is greater than or equal to 2. If n is not, then there is some other thing that I will tell you for general form of Newton's identity. Okay, so what is general identity? Please understand. Suppose you are given a polynomial equation, okay, that is x power n plus p1 x power n minus 1 and so on, constant term pn is equal to 0. Now we are defining a sequence SR by alpha 1 power r plus alpha 2 power r. Let me write it here, alpha 1 power r plus alpha 2 power r and so on up to alpha n power r. Okay, here you can see I have not multiplied coefficients like p and q to these alpha 1 power r, alpha 2 power r and so on, which was there in quadratic when I was taking n greater than or equal to 2. Okay, so here if your sequence is given by this, because here you are having n roots, so there will be total n terms. In quadratic there were only 2 roots, so we were having only 2 terms. Now first please focus on the second one, not on the first one, on the second one, and you will see if r is greater than or equal to n, r is greater than or equal to n, this satisfies this polynomial equation directly. You can see instead of x power n it will be SR, then p1 same coefficient and then 1 degree less, p1 SR minus 1, then p2 SR minus 2 and so on. Here last term will be pn SR minus n, before that it would have been pn minus 1 SR minus n plus 1, and that is equal to 0. Okay, so you can see if r is greater than or equal to n, then even this term will be having some S1, S2, S3 type thing. So there is nothing coming negative here. So when your r initial term of sequence, its degree r is bigger than or equal to n, then it is written directly as it is. There is no difference. But now there is a change. If r is less than n, if r is less than n, then what will happen? You will start with SR, then P1 SR minus 1, same thing, P2 SR minus 2, same thing, and so on. Similarly, S1 PR minus 1. Actually, you can see that every time this P1 R minus 1, their sum is R, P2 SR minus 2, sum is R. Okay, but because R is less than n. So there will be some point where S1 will come and this PR minus 1 will be there, but there will be few more terms after that. Okay, so till S1 PR minus 1 it is going absolutely fantastic, there is no difference till here from this to this, but after that when it is a turn to write S0, okay, then please say it is R into PR. This is R into PR. Okay, so the next coefficient would have been PR. It will be multiplied with R0 S0. Some of you may think that S0 would have been N, because in this sequence if all R are 0 0 0, so there will be 1 plus 1 plus plus N times, so N. No, it is not, it is R into PR. Please understand it. The proof of this I have given in my session notes. Please go through those session notes. The proof of this part is totally same as, is absolutely same as I have given you here for quadratic. Okay, but for this part it is little tricky. I will suggest that first you think over it, how it is coming, why R is coming, and then after PR there is no term. Okay, so this is the another a case of Newton's identity when R is less than N. Okay, I will show you through example. Okay, please see, suppose alpha, beta, gamma, delta are the roots of a biquadratic. Okay, and Sn we have defined alpha n plus beta n plus gamma n plus delta n. Okay, now first of all let's say R greater than 4, let's say R is equal to 6. So what will happen? I think it is direct. It should be A S6 plus B S5 plus C S4 plus D S3 plus E S2 equal to 0. So every time you are decreasing your degree by 1, 6, then 5, 4, 3, 2. Here degree was decreasing 4 to 3, then 2, then 1, then 0. So here also we are doing the same thing. So this was when R is greater than or equal to 4. But if R is not greater than or equal to 4, it is less than 4, what will happen? Suppose R is equal to 2. So we will be starting with S2 here. If I am putting R is equal to 2 SR here, so it will be A S2 plus B S1. Okay, now it is a turn to write S0. Okay, but dear all understand, instead of writing S0 you will be writing 2, this thing here, and this will be multiplied with the that desired coefficient that would have come here, that is C here, and that is equal to 0. So this is how your S2 S1 will be connected. Okay, here if R is 3, then what will be happening? I think A S3 B S2 plus C S1. Now when it is a turn to write S0, you will be writing this R is equal to 3, and whatever coefficient is supposed to come will come here, and that is equal to 0. Okay, now one more thing I would like to mention here, and that is if R is equal to 4, it is equal to 4, that the value of n, what will happen? A S4 plus B S3 plus C S2 plus D S1. Okay, now it's a turn to write 0. S0. As I said, instead of S0 we will be writing the value of R, that is 4. Okay, and then the coefficient that should come, so 4E equal to 0. When R is equal to 4, actually you can think of this 4 also as S0. There is no problem considering this as S0, because S0 will be 1 plus 1 plus 1 plus 1, 4 times of 4. So for this case we have included R greater than or equal to 4. Okay, so here if R is greater than or equal to n, even if this becomes 0, it is okay, because if it becomes 0 at the last term, then it is fine. But if it is becoming 0 before that, I have told you, you have to terminate your terms at that point only. You have to write the value of R, you have to write that coefficient that is supposed to come here. Similarly for R is equal to 3, R is equal to 2, whenever it is less than or less than n. Okay, so this is how for that first case, special case when R less than n should work here. Now important note, what is important note? First thing is that, as I told you, there are two cases. When R is greater than or equal to n, you can connect with what I have said just now. In this case, your sequence Sn can be this also, P1 alpha power n, let me take SR. Your sequence SR can be taken as P1 alpha power R, alpha 1 power R, plus P2 alpha 2 power R, and so on, plus Pn alpha n power R. Also works fine. I told you the proof of this thing in quadratic, same thing will be for any n degree polynomial. So even if you are taking SR, not alpha 1 power R plus alpha 2 power R and so on, you can multiply some coefficient also, that also it will work fine. Your recurrence sequence, recurrence relation will work fine. But if you are having R less than n, if R less than n, then only SR is equal to alpha 1 power R plus alpha 2 power R and so on, plus alpha n power R to be taken. Okay, why it is so? You can come to know about this through proof. Okay, the proof of this is separate, where you know we multiply and then add. So P1, P2, if it is there, that is also fine. But in this case, when R is less than n, then this P1, P2, P3 has to be 1, 1, 1 only. Then this will work. This was my second note actually. I have already taken. Now I will take one example before I go to previous year question. So alpha, beta, gamma are the roots of this equation. That's a very famous question. You must have done this before. Now I will do this question with the help of Newton's identities. Okay. So let me define S1 as, let me define SR. SR as alpha power R plus beta power R plus gamma power R. Okay, where alpha, beta, gamma are the roots of this cubic. Okay, now we are looking for that S5 upon 5 should be equal to S3 upon 3 into S2 upon 2. So that is the question. Okay, let us see how we can do it. Now in this case, you know, S0 will be 3. Okay, S1 is alpha plus beta plus gamma. I think here you can check x square coefficient is not there, so it will be 0. Okay, now using these two, you can find S3, S2 actually. Let us first find S2. Yeah, S2 is also needed. So if I start with S2, so first term is S2, and please notice R is less than n this time. So it will start with 2. So it will be then QS1. Now it's a turn to write. 1 minute, I have made a mistake here. The mistake here is that yeah, the mistake here is this is third degree term and the 2 degree term is not there. So if you're writing S2, so S1 will be multiplied with 0. You can say x square coefficient is 0. So 0 into S1. Now it is turned to write S0, and here I will be writing 2 because my R is 2 here, and the term, the coefficient that should have come here is Q. Okay, that is equal to 0. So from this you can directly say that S2 will be equal to minus 2Q. In fact, some of you may say, sir, this could have been done directly also, because we just have to do alpha plus beta plus gamma whole square, and that is equal to alpha square plus beta square plus gamma square plus 2 times alpha beta plus beta gamma plus gamma alpha. I think we can write that way also, S2. That is fine. But I am now finding S3, then S5 also. So S2 is found. Now we have to find S3. So if I have to start with 3, so S3, then 0 times S2 plus Q times S1 and R times S0, which is 3, you can say. Okay, both way I have told you it will be 3. Now S1 is already 0. S1 is already 0, so this will not come. So I think S3 is found directly minus 3R. Now this can also be found using algebraic identities, but not that faster. And then coming to S5. Okay, now if I have to find S5, so S5 plus 0 into S4 plus it will be Q into S3 plus R into S2 is equal to 0. Now I think we know many of them already. This will become 0. In fact, we have not found S4, and because of this thing here in the question, this coefficient being 0, S4 is not needed actually. So S5 plus Q into S3, where is S3? Yeah, minus 3R. Okay, plus R into S2, S2 is minus 2Q. that is equal to 0. So what we are getting, S5 is coming out to be 3 plus 2, 5QR. 5QR. Okay, so S5 is equal to 5QR. I can write S5 upon 5 is equal to Q into R. Then what is Q and what is R? You can see Q is S2 upon minus 2, S3 is R is S3 upon minus 3. I think we are done. We can also write this as S3 upon 3 into S2 upon 2. S3 was minus 3 into Q. Let me just check. Yeah, minus 3 into R actually. Minus 3 into R. And S2 was minus 2 into Q. So you can see how fast it has been found. Okay, now let us try to use this Newton's identity in few of the previous year question, JEE advanced question. Okay, I think this is 2017 question. It says let P and Q be the integer, alpha beta are the roots of the equation x square minus x minus 1 equal to 0, where alpha is not equal to beta. Okay, and n is equal to 0, 1, 2. An is equal to P into alpha n plus Q into beta n. So you can see same expression, same sequence they are talking about, which I was also talking about. Now they are asking 8, 12. Now I think that can be the easiest question so far in the history of JEE Advanced, if they are asking S12 in terms of A11 and A10. So isn't it very direct that A12 minus, because coefficient is 1, so A11 minus A10 is equal to 0. So your answer is directly A11 plus A10. Done. Okay, now if we have to find the second part, A4 is equal to 28 and we have to find P plus 2Q. They have also mentioned few things, that P and Q are integers, and they have given some fact that if A and B are rational numbers, irrational numbers, A and B are rational numbers, and you have written A plus B root 5 is equal to 0, then A is equal to 0 and B is equal to 0. You can see that this thing is very obvious. I think you do it in 10th standard also, but they have mentioned it here so that there is no ambiguity. Now A4, from this sequence, can I not directly write A3 plus A2? In fact, that is corresponding quadratic to your Fibonacci sequence. Fourth term is sum of previous two terms. Okay, A3 can be written as A2 plus A1. Okay, A2, let me write A2 only here. So you get 2 times A2, and now A2 I will write A1 plus A0 plus A1. As I told you, A0 also works well here. Okay, so my A4, which is 28, A4 which is given to be 28 is equal to 3 times A1. And what is A1? A1 has to be P alpha plus Q beta. Okay, and what should be A0? A0 means it should be 2 times A0 actually. So it should be 2 times P plus Q. Okay, so this becomes 3 alpha plus 2 into P plus 3 beta plus 2 into Q. Okay, now here we will need alpha and beta also. Please see, if you solve alpha beta, I think by quadratic, simple quadratic formula, it is minus b plus minus under root of, I think 1 plus 4, so 5 by 2. So alpha beta are both irrational numbers. In fact, they are irrational conjugates, you know, irrational parts differing with plus minus sign. So if I put 3 alpha plus 2 or 3 beta plus 2, this root 5 term will also come there. Whereas you can see on the left hand side it is 28, which is a rational number. Okay, if I write it completely, I think 3 alpha plus 2 will be 3 alpha plus 2 has to be, if I take alpha with plus sign, okay, so it should be 3.3 by 2, so 1.5 plus 2. 1.5 plus 2 is how much? 3.5. Okay, plus this will be 3 root 5 by 2. So 7 by 2 plus 3 root 5 by 2 into P. And in this case, it will be just 7 by 2 minus 3 root 5 by 2 into Q. Now, as they have mentioned here, I think you cannot get rid of these root thing unless P and Q are equal. because on the left hand side it is rational number. 7 by 2 when multiplied with p and q, where p and q are integers, they can give you only rational number, but unless p and q are equal, they cannot be cancelled. So I'm concluding that p is equal to q. And if p is equal to q, okay, what we are getting here, I think if you take p and q equal, I think I'll use one step before. Actually, I wrote this term only to explain you why p is equal to q. If you can understand without writing, then there is no need to write this term actually. So if p is equal to q, so you can see your 28 will become equal to p and q can be taken common. P and q are equal, so this will become equal to 3 alpha plus 2 plus 3 beta, 3 alpha plus 2 plus 3 beta plus 2 into p. Okay, here 28 equal to, and 3 times alpha plus beta, sum of roots is 1, so alpha plus beta is 1 plus 4 into p. So from this we get p to be equal to 4 and q is also to be equal to 4. So p plus 2q they are asking. So I think that will be equal to 12. Yeah, 12. Okay, so this is how this question can be solved if you use Newton's identity. In fact, because A4 they are giving you, I think it can be done with the help of Weierstrass relation also. Alpha plus beta we know, alpha square plus beta square can be found. Using that, alpha power 4 plus beta power 4 can also be found. But there is no problem with this method also. In fact, A12 I don't think anyone will be doing by some other method. Actually, there is some method where we multiply this with alpha plus beta and then we eliminate and do some solving. That way also you do it. But this kind of question has been asked so many times that it is mandatory that we know this thing. Okay. Now one more question in JEE Advanced 2019, and the interesting thing is the quadratic is same. Alpha and beta are the roots of this same quadratic, x square minus x minus 1, with alpha greater than beta. For all positive integer n, we define an as alpha power n minus beta power n upon alpha minus beta. Okay, now please understand first, this an is also of the same form. An can be written as p into alpha power n plus q into beta power n. Here p is 1 upon alpha minus beta and q is actually negative of it. And because of it, you can write a few values like a naught. If you put n is equal to 0, so that will be 0. A1, I think alpha minus beta upon alpha minus beta, so 1. A2 also, if you want, it will be alpha square minus beta square upon alpha minus beta, so alpha plus beta will remain, so it will be 1. So these three terms are very easy to find, so let's write them. Okay, now what are they asking in the end? They're asking in the A option, A1 plus A2 plus A3 up to AN is equal to this thing. Now how we can do this question? Let me see how many slides I'm having. I will use one slide in between. Okay, so our quadratic equation is x square minus x minus 1 is equal to 0. So here an plus 2 will be equal to an plus 1 plus an. An plus 2 minus an plus 1 minus an is equal to 0. So I can write like this. Then an plus 1 will be equal to an plus an minus 1. An will be equal to an minus 1 plus an minus 2, and so on. You can write it a2 equal to a1 plus a naught. Okay, now if you add all these terms both sides, you can see when you will be adding, this an plus 1 will cancel this an plus 1, this an will cancel this an minus 1 will be cancelling the next term. Okay, in fact a2 will be coming here, which will cancel it here. So if you add all these things, okay, if you add all these things on the left hand side, it will be just an plus 2, whereas on the right hand side it is just a1 here, and this entire thing is intact, which is actually a1 an plus an minus 1 and so on, plus a1 plus a naught. Okay, and what we are looking for here, a1 plus a2 up to an. So we are looking up to this thing, an plus an minus 1 plus a1, and that will be equal to an plus 2. This will be equal to what we are looking for. We are looking for r from 1 to n. That will be equal to an plus 2 minus a1 minus a0, minus a1 minus a0. As I told you, a1 is I think 0. No, a1 is 1, a0 is 0. Yeah. So it will be an plus 2 minus 1. I think this is what A option is also saying. So A option is correct. A option is also correct. Okay. Now coming to B part, or maybe I can come to C part also before that. Yeah, let's say C part, because in between they are actually defining another sequence of Bn. Okay, you can find out with the help of An that Bn is also satisfying the similar recurrence relation. Although here I will be using some other method, or let me do both actually. So we are given Bn is equal to this thing. So let me know if I can write An minus 1 as an minus 2 plus an minus 3 using that relation I told you, because all an should be satisfying this quadratic. So an minus 1 will be equal to the sum of next two, or sum of previous two actually. Similarly, an plus 1 would be sum of previous two, that is an plus an minus 1. Now if you combine them, an minus 2 with an minus 2 with an, you can see this will be, I think, let me write it directly. This will be Bn minus 1 and the other two will be Bn minus 2. You can check. So you can see this Bn will also be having similar recurrence relation among them. So this will be satisfying same quadratic. So this Bn should also be coming from P into alpha power n plus Q into alpha power Q into beta power n. Okay, now we have to check for this option whether my P and Q are 1 or not. We just have to check whether P and Q are 1 or not. Now to check that, I think we may use initial values of B1, B2. So B1 they have already given as 1. Okay, so if B1 is 1, so you can see if this relation is to be valid. Okay, so alpha plus beta has to be 1, which is actually the case. So B1 is actually satisfying this relation. Okay, let me repeat what I'm doing. I'm not solving for P and Q. You can do it for this also, but what I'm saying that if this option is to be correct, my P and Q has to be 1 and 1. I'm just verifying whether this is true or not true. Okay, so if B1 is given 1, so this B1 has to be alpha plus beta, which is actually true because alpha plus beta is 1. Okay, so this relation is true for n is equal to 1. Okay, now we can find whether it is true for n is equal to 0 also, 0 or not. So B naught, if we have to find, okay, how we can find B naught? Let us find, actually from this B naught will be 2. From this if we go, B naught will be 2, just let me think, and B2 would be alpha square plus beta square. Okay, now alpha square plus beta square, if you solve, it will be, you can find by sum of roots, product of roots also, that will be 1 minus 2, 1 plus 2 actually, so it will become 3. Sum of root square, so 1 minus 2 times product of roots, this which is minus 1, so it is 3. Now you can see whether this B2, B1, B naught are satisfying this relation or not. Which relation I'm talking about? Bn relation. So you can see this B2, which is 3, is satisfying B1 and B0. 1 plus 2 is equal to 3. Now I will summarize what I'm trying to say, that I'm not finding P and Q. I'm only saying whether P and Q equal to 1, 1 are satisfying this or not. So with the help of this P equal to 1, Q is equal to 1, if I take C option, my B1 should be 1, my B0 should be 2, okay, my B2 should be 3. Okay, and you can see this B0, B1, B2 values are satisfying this recurrence relation. That means the solution of this would be of the form P alpha power n plus Q beta power n. Here P and Q will be 1, 1 only. Okay, if you solve it by using these values, you will have to find value of alpha beta also, which I have avoided by doing this method, by going with this method. So that is the difference. I will come to B and D, and please listen carefully how B and D I am going to do. But before that, I will like to tell you one more method to prove that Bn is equal to alpha power n plus beta power n is true or not true. Okay, please see. Here Bn, they have given an minus 1, that will be alpha power n minus 1 upon alpha minus beta. I am only writing alpha term, beta term will be similar. Okay, plus an plus 1 will be alpha power n plus 1 upon alpha minus beta, minus same calculation for beta also, minus same calculation for beta also. Here you can see it will become alpha power n upon alpha into alpha minus beta. Okay, and here this will be alpha into alpha power n upon alpha minus beta, minus same calculation here also. So you can see this, if you take LCM, becomes alpha into alpha minus beta, which I can write alpha square minus alpha beta in denominator, and that will be alpha power n common, and this will be 1 plus alpha square. Okay, same for beta also. Okay, alpha n common, and this alpha will multiply, so alpha 1 plus alpha square. Here you can write this as alpha n. This alpha square will be equal to 1 plus alpha. I can write it directly. And alpha beta product is minus 1, so minus plus, it will be 1. And here alpha square, again you use similar way, it will be 1 plus alpha. Okay, so you can see this 2 plus alpha is getting cancelled. Same will happen here also. So you are getting alpha power n plus beta power n. Okay, so this is also how you can do it. Okay, now coming to this B and D part together. Very interesting. Please see how we can do it. You can do it by GP, which most of the people have done it, but I will do it some different way. Please see how I'm going to do it. Now please understand, my an was some p into alpha power n plus q into beta power n. Okay, but here we are looking for summation of an upon 10 power n. We are looking for summation of an upon 10 power n. We can write this as p into alpha upon 10 whole power n plus q into beta upon 10 whole power n. Okay, so the sum of these terms of this sequence is like where roots should have been alpha by 10 and beta by 10. Alpha by 10 and beta by 10. Okay, now please understand, for the sequence an, this p and q were 1 upon alpha minus beta and negative of 1 upon alpha minus beta. In case of B series, the p and q are just 1 1. If you replicate the same calculation for this also, then p and q are just 1 1. Okay, so what I am now going to do, I will make a quadratic using this, whose roots are alpha upon 10 and beta upon 10. Okay, and you know from transformation of roots, if I want to make this kind of quadratic, I will replace x by 10x. If you replace x by 10x, then your roots, which were earlier alpha beta, will be converted to alpha by 10, beta by 10. That's a very important thing. Please understand, if you replace x by 10x, so your roots in terms of 10x will be same alpha beta, and if you solve it for x, it becomes alpha upon 10 and beta upon 10. So my quadratic now will be 100x square minus 10x minus 1 is equal to 0. Now this is the quadratic which should be satisfied by an upon 10 power n sequence. Okay, if I call this sequence as Sn, let us say for time being, for Sn. Okay, so what we are looking for? We are looking for summation Sn and ranging from 1 to infinite. Okay, now if I keep putting this Sn here, so my first term can be 100 S2. I will start with S2 minus 10 S1, or let me write it as equal to plus S0. Okay, what will be S0 here? S0 will be P plus Q. Okay, S0 will be P plus Q. In case of An, P plus Q is 0. Please remember it. I'll come to that. And then if you put Sn is equal to 3, so that will be 100 S3 is equal to 10 S2 plus S1 here. and you keep on doing it. Okay, now if we keep on doing this till infinite, there is no need to write the last term. If you keep on doing like this till infinite, the sum here will be 100 into S2 plus S3 plus S up to infinite. Okay, on the right hand side it will be 10 into S1 plus S2 and so on till infinite. Okay, and the last one S0 plus S1 and S2 and so on till infinite. Now listen carefully. We are looking for this sum which is starting with S1, S2, S3 up to infinite. Okay, so here let me see, this thing here is actually this summation. Let me call this as S, capital S. So this capital S, if you look at this, it is one term less. So I can write this thing as 100 into S minus S1. This you can write it as 100 into S minus S1, whereas this is precisely 10S. Okay, this one is precisely 10 times S, and this is having one extra term S0. So this will be just S0 plus S. Okay, I take S on the other side, so it will be 89 into S here, and that will be equal to 100 S1 plus S0. Okay, now you can do these questions together now if you know what is S1. Okay, so S1 in case of first series, S1 means it will be A1 upon 10. A1 upon 10. Okay, and A1 upon 10, as I have already told you, A1 we have I think found. A1 was the A1 we found, it was I think 1. I think I could have done here also. So A1 was 1, so this will be 1 upon 10. So if you put 10 here, okay, and AS0 will be A0 upon 1, and A0 is 0, you know it. So from this, for this B option, this S coming out to be I think 100 upon 10, that is 10 upon 89. So this is correct. This option is correct. Now if we do it for D option, in that case your S1 will be B1 upon 10, and B1 means, because B is alpha plus beta, B1 is alpha plus beta, so that will be 1 upon 10 only. But your S0 means it will be alpha power 0 plus beta power 0, so it will be 2. Okay, here S0 was 0, here S0 is 2 for the series Bn upon 10 power n. So here that sum will be, so let me do this calculation here, just small part is required. So that sum will be from here, because this up to this point all the calculations were same. This was for B part, this is for D part. Here it will be 89S is equal to 100 S1 means 10, and S1 will be S0 will be 2. So from there you are getting S equal to 12 upon 89. 12 upon 89, and this is done. So I hope you understand that these two parts are done directly with the help of recurrence relation only, and in fact I have solved both of them almost together. Till this point they both were having same calculation. For B part it was different, for D part it was slightly different, so answers were different. B option is correct, D option is not correct. So final answer was that should have been A, B and C. Okay, now coming to one question that is I have taken from JEE Mains, although it is from JEE Mains, but this was one of the I will regard as a difficult question. Okay, please see why I am calling this a difficult question. So first of all, they are giving alpha beta are the roots of a quadratic which is involving iota. Okay, then they are asking product of 16 into real part of some expression into imaginary part of same expression. Okay, now if you look at this alpha power 19, beta power 19, it looks like a sequence S19, then S11, S15. But the thing is, there is a difference of degree of 8 here, 19 to 11 and 15. The difference here is 4. Okay, so maybe we have to do something so that we can get relation between S19, S15 and S11, that is at the difference of 4. Okay, so what I am going to do, please listen carefully. I will be creating another quadratic whose roots will be alpha power 4, beta power 4. Okay, so if you write S1, if you write S2 in terms of alpha power 4, beta power 4, that will be alpha power 4 plus beta power 4. This will be alpha power 4 whole square plus beta power 4 whole square. So alpha power 8, beta power 8. Okay, so here between two consecutive sequences, the difference of powers of alpha and beta will be 4, 4. So that will help you to solve this question here. Okay. So please see how I am going to do this question. So my quadratic is 2z square minus 3z minus 2 iota equal to 0, and its roots are alpha and beta. 2z square minus 3z minus 2 iota, 2z square minus 3z minus 2 iota equal to 0. Okay, now if I want to create a quadratic whose roots are alpha power 4, beta power 4, what we do, we first replace z with root z. So my roots will become alpha square, beta square. So we will be writing it as 2z minus 2 iota is equal to 3 into root z. Now to make it quadratic, we will be doing squaring both sides. Okay, it will become 4z square minus 4 minus 8 iota z, and that will be equal to 9z. Its roots will be alpha square, beta square. Now we want roots to be alpha power 4, beta power 4. So if I write this as 4z square minus 4 is equal to 9 plus 8 iota z. Okay, now once again use the same transformation. I write it as 4z minus 4, and that will be equal to 9 plus 8 iota into root z. Then its roots will become alpha power 4, beta power 4. Do the squaring both sides. Okay, we will be getting 16z square plus 16 minus 32z. 4 into 4, 16 into 2, 32. Yeah. And on the right hand side, whole square of this will be 81 minus 64. I think it is 17. And plus 9 into 8 into 2, I think 144 iota into z. So if I bring everything this side, it will be 16z square minus, I think 49 plus 144 iota z plus 16 is equal to 0. Now its roots are alpha power 4 and beta power 4. Okay, now here you can say that if I make a relation like this, okay, relation of S1, S2, S3, then there will be a gap of powers of 4. Okay, now I am going to use this. Please understand how I am going to use it. Now because I said this alpha power 4, beta power 4 should satisfy it. Okay, because they are roots. So I can say 16 alpha power 4 plus 16. I am writing slightly different way. Okay, and I'll bring that on the other side. Actually z is outside, so that will be 49 plus 144 iota into alpha. 16 alpha power 4, sorry, 8 actually, not 4, it will be 8 because alpha power 4 is the root. So it will become 16 into alpha power 8 plus 16, and that will be equal to 49 plus 144 iota alpha power 4. Similarly, we can write it for beta also. So beta power 8 plus 16 is equal to 49 plus 144 iota beta power 4. Now what I am going to do, I will be multiplying my first equation by, I want here 19, 11 and 15. So to make it 19, I will be multiplying this by alpha power 11. I am not having space here, but let me write it here. I will be multiplying it by alpha power 11. Alpha power 11 I will multiply, and I will multiply this by beta power 11, and I will add them. If you do that, we will be getting 16 times, I think 16 is common from all of them. So it will be alpha power 19 plus beta power 19 plus alpha power 11 plus beta power 11 on the left hand side. Whereas on the right hand side, I think you can take 49 plus 144 iota common. Okay, and we will be having alpha power 15 plus beta power 15. think my writing is not that good here. Alpha power 15 plus beta power 15. Okay, now can you see it that we have found this expression alpha power 19 plus beta power 19 plus 11 alpha power 11 plus beta power 11 whole divided by alpha power 15 plus beta power 15. So we have got this to be alpha power 19 plus beta power 19 plus alpha power 11 plus beta power 11 whole divided by alpha power 15 plus beta power 15 will be equal to I think 49 by 16 plus 144 by 16 iu. Now what they were asking? They were asking the product of 16 into real part of it, which is 49 upon 16, into imaginary part of it, 144 upon 16. So this 16 gets cancelled, 16 cancel this 9 times I think. So 49 into 9, I think it is 441. I think that is the answer of this question. People have done it otherwise also, but I am just trying to connect this question with my method. Here there is extra thing we have done. We have used the transformation. In fact, I have taken 2 more questions where also I will be using the same thing, and it's a very powerful thing that you transform so that your difference of power is matching. Okay, and then use this concept of Newton's identity. Although here it was not directly Newton's identity, but it was something that we used while proving the Newton's identity for quadratic. So one more question. I think this is very direct question here. Here we are given Pn is equal to alpha n plus beta power n. Alpha power n plus beta power n. P10 they have given, P9 they have given, P8 they have given. Okay, we know what is the direct relation between 10, 9 and 8. Then they have given P1 also. Now if alpha and beta are different, they should have been different actually. If they are different, then this Pn will be satisfying the quadratic, let's say ax power 2 plus bx plus c equal to 0. Okay, because P1 is 1. P1 means sum of roots only, because we are given this alpha n plus beta n. This will be equal to minus b upon a, and that is equal to 1. So my b value is minus a. So I will write this once again. It will be ax square minus ax plus c equal to 0. Now you put these values of P10, P9, P8. So it will be 123a minus 76a, because this is 10, then 1 degree less, then 1 degree less, plus c into 47 is equal to 0. I think 123 minus 76 is also 47. So c is coming out to be minus a. C is coming out to minus a. So the quadratic is x square, because a minus, I think b is minus a, so x square minus x minus 1 equal to 0 will have roots as alpha and beta. Now they are asking roots to be 1 upon alpha, 1 upon beta. I think we just change the order of the coefficients. So minus 1 will come here, then minus x plus 1 is equal to 0. So that will be the final answer of this question. You can multiply by minus 1 to match your option. I think this is also important. Whenever roots are reciprocal of your original equation, then you just have to reverse the coefficients. Constant term will become leading, second lowest term will become second leading term, and so on. So here also I have done the same thing. Minus 1 has come with x square, this minus 1 will come with x, and this 1 will come with as a constant. So this is how we have done it. Now without that, I think you can do it, but this will be lengthy. I think this is very intuitive if you know the Newton's identity. After that it is direct. Actually those who do not know about Newton's identity, they have to prove it in the question, so that this makes the length of your solving bigger. But as it is coming so frequently, it is highly recommended that you remember it. One last question here, please see. Alpha and beta are the roots of this quadratic, and roots you have to find the quadratic whose roots are alpha power 4, beta power 4, alpha power 6, beta power 6. Now one of the method is that you start with alpha plus beta, then alpha square beta square, then alpha power 4, beta power 4, alpha power 6, beta power 6. You can do it, but what I will suggest here is that I will use once again the transformation. If I transform x with root x, it will be x minus 1 is equal to minus 2 root 2 x, 2 root 2 root x actually. this will go that side, and then you square it to make it quadratic. So it will be x minus 1 whole square is equal to 8 into x. So this time it will become x square minus 2x minus 8, so minus 10x plus 1 is equal to 0. So this will be having roots as alpha square beta square. Okay. Now we are looking for alpha power 4 beta power 4. If I define a sequence Sn, that is alpha square power n plus beta square power n. Okay, so we are looking for S2 here. We are looking for S2 here. So I think this S2 will be plus 10 times S1 plus S0. S0 you can write it as 2 also. Actually, this will be with minus sign. This will be with minus sign because this 1 will go that side. S2 will be 2. Now S1 is how much here? S1 is I think 10. So 10 into 10, 100 minus 2, 98. So this value is 98. Okay, now we are looking for S3. Please connect with this. Now if you want to know S3, it will be S3 minus 10 S2, or you can write 10 times S2 and minus S1. If you take that on the other side, now S2 we have find 98, so it will be 980, and S1 value is 10 here, so it will be minus 10. So this gives you 970. Now this will be 97 because divided by 10 will give you 97. Then you know how to form quadratic. Sum of roots will come with coefficient of x. So 98 plus 97 is 91, 95. So maybe this or this. And then product of root, you have to multiply these two. You can check which one is correct. Probably A is correct. Okay, so here also you can see this power 6 plus beta power 6 term, this power 4 term we have found. First we did transformation and then we use the Newton's identity. Some of you might not be comfortable with transformation, so please go through your book. Maybe it is given everywhere. If you have to find roots which are alpha square beta square, then x replaced with root x. In fact, let me give you a few ideas. If roots are alpha beta and you want 2 alpha 2 beta, then in your equation x will be replaced by x by 2. It is actually reverse of this, you can say, in a way. Alpha by 3, beta by 3, then your x should be replaced by 3x. If you want alpha square beta square, then it should be x replaced by root x. And then do squaring properly so that you get a proper polynomial. Okay, this is what I have done here. In fact, I have done it here also, and I have done in this question also 2 times. Okay, and then this question becomes very easy. Otherwise, you may find how you will do this question. So this is all for today, bachcho. This was all for today's session. I'll come in with new subtopic. I'll decide which topic. Okay, thank you so much. Take care. Bye, bachcho.